All right, hey everybody. Oh, got ya. All right, hey everybody. Sorry if I just burst your eardrums. I have my phone on my desk so I can see what you guys are seeing. So if there's any delay, I can detect it. But I forgot to mute my phone. And half of you probably can't even hear me because you're already deaf. I apologize for that. But today, we're gonna do more of what we did on Monday. We're gonna do some cylindrical and spherical stuff just as a quick review, and then we're gonna get into some Jacobian coordinate transformations. Which are really nice. I honestly think probably one of the more easier sections of this whole unit is the Jacobian stuff, which is nice. So hopefully this will be a really nice. I'll give you guys a lot of chances to do some math, get a lot of problems right. Should be a good time. So let's go right into it, start diving into it. From fall 2019 exam 3 review session, it asks to find the integral of the function, as you can see here, over the region between the spheres of radius 2 and 4, centered at the origin. So I'm going to let you guys run off on this right away, see how good you can do. Don't necessarily worry about solving the integral, just find the integral, set it up. We're going to be looking for obviously something in spherical coordinates. Remember spherical coordinates, so if you need to pull up your notes from last session, do that. But it'll be a triple integral of the surface. There's going to be some dv, and we're looking for an integral of the function, so f of something. I'll give you guys like 2 or 3 minutes. Draw the region, see if you can get it. I believe in you. Call on your knowledge from last time, and we'll see how you do. Good luck. I'm setting a timer for 2 minutes right now. All right, sweet. So that was 2 minutes right there. So let's take a look at how you guys did. Let's go ahead and draw the region, because that's probably a good place to start. I guess we should probably do this, shouldn't we? Let's draw it like this. Okay, so it's a sphere of radius 2 and 4, and we're looking for the integral of the region between those two spheres. So we'll have one sphere, say that's radius 4. We'll have another sphere on the inside, radius 2, and we're looking for everything in between those two spheres. So if we write our integral, we'll have our 3 integrals, and we'll have dv function. So let's convert our function to spherical coordinates first. I think that might be easier. Doing that, I apologize if the microphone's getting scratchy. I'll fix that. There we go. So converting our function into spherical integrals first, let's do that. So we'll take this guy. Obviously, this is just going to be rho to the -3/2. Or rho squared, excuse me. Rho squared to the -3/2. Which would then just be rho to the -3rd. So we'll have rho to the negative third on the inside. And now remember we're going to spherical coordinates, so it's rho squared sine of phi d rho d phi d theta. Okay, so now we're concerned about theta. Let's start with theta. What are our bounds for theta? I'm going to have you say it out loud. You don't have to unmute yourself. Just say it to yourself. It is 0 to 2 pi. Good job. Yep, 2 pi. Okay, now let's do phi. Phi is from 0 to, yep, pi. I heard it all. Everyone said pi. I heard it. Nice job. Okay, now let's do rho. So rho, remember rho is the radius, and I'll make it nice and color coordinated for you guys. So we've got d rho. Fix the d. In rho, we're starting from radius 2, and then we go out to radius 4. So it's that region we care about. So that means rho is going to go from 2 to 4. Which then, of course, our integral simplifies. Whoa, that's kind of cool. Our integral simplifies into 0 to 2 pi, 0 to pi, 2 to 4 of 1 over rho sine of phi d rho d phi d theta. Cool. Are there any questions about that? Any at all? And now, of course, you would solve this, and I have the answer to solve it. I'll probably gotta just save you the time. But in case you want to do the practice, oh, you know what? I don't have the final answer. But you could try it for yourself, so it probably wouldn't be too hard. Let's move on. That was just a warm-up. So let's look at the next one. Convert the integral of this guy from cylindrical coordinates to Cartesian coordinates. Okay, cool. So we're going from cylindrical to Cartesian. That's kind of fun. So let's convert, draw our xy slice and graph and label the level curves. Then convert z to Cartesian. Remember our cylindrical bounds are going to be z goes from 0 to the square root 3r. Convert that to Cartesian. And then see if you can write the integral. I believe that you guys can do this xy slice. So remember we're concerned about the xy. Yeah. I'm going to mute this again, and we'll see how you guys do. I'll set another timer for 2 minutes. Good luck. Hopefully your cylindrical coordinates practice is going to pay off. All right, I'll be honest, I forgot to set a timer for that one. So I'm going to guess it's around 2 minutes for this. So we'll see how you guys are doing. Okay, so drawing the XY slice graph and labeling the curves. So let's start from the outside in like we would drawing these. Theta goes from 0 to pi, which in degree talk is, you can say it out loud, 0 to, 180 degrees. So we're moving like that, right? 180 degrees, 0 to 180 degrees. And that whole sweeping motion, our radius is covering from 0 to 1. So that would be our radius. So like our radius is 0 to 1 all the way through. So our region looks like, say we say 1, 2, 3, 4, 5. Let's say like that's 1. There's 1, right? That's 1, 0, 0, 1, negative 1, 0. Got a nice big arc like that. So that's our XY level curve. So now we want to label that curve. So of course that's going to be a circle, which is x squared plus y squared is equal to 1, right? This is a circle with radius 1. We could also say that like y is equal to the square root of 1 minus x squared, or vice versa, x is equal to the square root of 1 minus y squared. I think we'll just stick with that though. Okay, cool. So we've labeled that curve. Converting part B, our z to Cartesian. We don't have to do anything with the 0. It just stays at 0. And we have a radius. So remember that in cylindrical to Cartesian, it's x squared plus y squared. That's what your radius is, which is also to like the square root of 3x squared plus 3. We could do either. Either is fine. Okay. And then our last step is just to write the integral. So let's do that. We'll do it in another color. So we're going from, I guess we should start with our function. So r squared theta, sine of theta, we can convert that if anyone can think about it. Think about it. Anybody? Anybody? Think about it. Well, we know that, remember that y is equal to r sine theta. Right? Is that correct? So we'll have, so we'd have an extra r. So it'd be r times y sine, and then that sine of theta would go away. All right, cool. Cool. So we have an r times a y, and now the trick is, so remember that dz, dr, d theta is equal to dx, dy, dz only if there's an r on that side. Now that there's an r on that side, that's where our other r gets canceled from. So now we just have a y. So on the inside, we have y, and we could choose any direction we want. Let's keep it like dz, dy, dx, because I think that might help us best in the long run. Okay. So now we just have to get our bounds. We started with our x. Our x just goes from, you can look at it on our graph, right? It goes from -1 to 1. Our y, we go from, so now we need a line, and we wrote that equation right here. We're going from 0 to the square root of 1 minus x squared. And then lastly, for our z, we're going from 0 to, and we just drew the bound right here, square root of 3x squared plus 3y squared. Cool. Now that we drew our bounds, that's our final answer. Of course, we could solve that if we wanted to, but I don't even think the question asked for us to solve that one. But it would just be a triple integral if we did. Cool. Are there any questions about that? Sweet. All right, cool. I'll get rid of that just so it makes sense when I release it on the website. All right, let's move to the next one. Now we get into some Jacobians. Okay. So we talked about this. The reason we do the Jacobian matrix and the reason we do coordinate changes is so we can play with shapes that aren't necessarily in Cartesian space. And maybe you'll do things with this, maybe you won't. In aerospace, we do it like, say you have a wing and it's not like a box, and you want to integrate, like, say, like the lift over the wing. You still might want box sections. but those box sections are going to compress as the wing gets smaller. And of course, like I'm doing a terrible job drawing it, but like you can see, every box wouldn't necessarily be the same shape. So remember, we saw in lecture they had some really great graphics of in those coordinate switches, you can have weird shapes, but they stay boxes. And then when you spread it out into Cartesian, those boxes look like they normally would, and your integration is really easy. So a lot of real world applications, and I've seen proofs of it in textbooks, and maybe had to do it on an exam once or twice, not in Calc 3, but in other classes. But this is more real world stuff that we're doing in Calc 3, so it's really cool. The steps to solving the variable problems, remember, 1, identify the substitution, but like we talked about in lecture, if you saw a lecture, it's usually just given as u is equal to something and v is equal to something. I've never seen them have you solve for u and v, so which is really nice. Jacobians. So the Jacobian matrix, remember, it's the determinant, well, the absolute value of the determinant of, basically, it's like rho x over rho u, rho x over rho v, rho y over rho u, and rho y over rho v. Or you could just say it's like u of x, u of v, y of u, y of v. In that order, as we'll probably see as we go on, isn't necessarily all too important with what we're going to do. So you can change that order because you're taking A, the determinant, and then B, the absolute value of that determinant. It's not too important what the order is, but we'll get to that. Rewrite the function in terms of u and v, which is pretty easy. So you take your function, you just basically take your f(x) of y, and you change it to a function of u and v as best you can. And then determine your new bounds. That takes from drawing the picture. Draw a picture, list your inequalities, and then make substitutions as you need to. And we'll get plenty of practice. You won't even have to memorize that process because you're going to do it so often. Okay, and combine everything together. Just throw it all into a triple integral that you need to, or a double integral. So let's look at it. Here we go. Find this integral by doing a change of variables, and you can see I list everything out for us, what the steps are. Maybe we can just go through this one together, and then I'll let you guys loose on the next one. So let's do, first step, we need to identify what the substitution is. They give us to us y minus x squared, and we also get v is equal to x. Okay, now we need our Jacobian matrix. So looking at our Jacobian matrix, it's going to be the absolute value of the determinant of, let's see, we'll have, take the partial, let's do, I guess we can write it out, excuse me, be ux, uv, and then it'd be, ux, uy, and then vx and vy. So, which is going to equal, so take the partial u, partial x, negative 2x, partial u, partial y, which is just 1, partial v, partial x, which is 1, and then partial v, partial y, which is 1. So we'll get the determinant, we'll get the absolute value of, now we take the determinant of the inside, so we get negative 2x times 1 minus 1 times 1, which is equal to negative 2x minus 1. I made a slip up somewhere because it should just be, that there should be a 0 in there. Oh, partial v, partial y. There's no y in the v equation, so it should just be, yeah, thank you, Nathan, I just saw it, yeah. This should be 0. Okay, cool. And then this turns into 0. So then we just get negative 1. Absolute value of negative 1, which is just equal to 1. All right, cool. Which means that du dv is equal to dx dy. So our conversion is really easy. So I guess we don't have to play with that this time. Okay, let's convert our function. So our function, remember, usually the function switch is pretty easy. You can see that right there is also this guy right here up in the top. U is equal to y minus x squared. So our function just becomes 6x over 1 plus u cubed. And then we have an x on the top. We can see that v is equal to x. So that just says 6v over 1 plus u cubed would be our function. All right, cool. The bounds, The bounds are always fun. You guys saw in lecture, you'll remember this shape if you saw the lecture this morning on bound switching and changing of variables. So now we have to, let's do UV first. So if we do, and I'll scroll this up because my computer's going to get mad at me if I do stuff at the bottom of the screen. So our UV, we have U is equal to y minus x squared, and V is equal to x. So, oh, excuse me, we'll do our xy graph first. I'm getting ahead of myself. So we'll start with our xy graph. Okay, so let's look at our bounds. Our bounds are x squared plus x to x squared plus 1. So let's draw the x squared plus x and x squared plus 1 graph. If you saw the x squared plus x graph, it goes through the origin, right? And then all we care about is up to x is equal to 1. So we'll do 1, 2, 3. We'll say like this is x equals 1, 1, 0 right there. And it goes like this. Oh man, my drawing is so bad. So we'll go up to 4. So it'll look like that. And that is y is equal to x squared plus x. Or is it minus x? Yeah, x squared plus x. Now x squared plus 1 is just a parabola that passes through 1, right? So x squared plus 1. So we got 1 right here. And then it will go up like that. X squared plus x and x squared plus 1. I guess we have to see where they intersect. At 1, it would become 2. So this should actually go up to 2. So that goes up to 2. 1 comma 2. Here's your y is equal to x squared. And now we've got, this is x is equal to 0, that line right there. And now we need to convert basically that graph and all of those different bounds into a UV graph. So like we saw in lecture, our 3 inequalities are right here, right? We've got this one, and this one. So we'll have x is equal to 0, y is equal to x squared, and y is equal to x squared plus x. Usually just outlining them like that makes your life the easiest. We'll take this. Of course, that just means v is equal to 0 because v is equal to x, like we have. Our next one, we have y is equal to x squared. So we can take that. Let's see how we want to do that. So remember that our inequality u is equal to y minus x squared. That's one of them. And I see that y is equal to x squared, so we can manipulate that. If we just bring the y to the other side, then we have 0 is equal to x squared minus 1, or minus y. Or the other way around, y is equal to y minus x squared. 0 is equal to y minus x squared. So that means that u is equal to 0. So if v equals equal to 0, u is equal to 0. Now we just need to find the line. Usually it's either going to be a straight line like a triangle, or it'll be a parabola. We don't really have much in between when it comes to these problems. So y is equal to x squared plus x. We can think about how we want to manipulate that. We have a u is equal to y minus x squared. So we bring that x squared to the other side. Then we can say that u is equal to x, and remember that v is equal to x, so that means that u is equal to v. Okay, so we have 3 lines, and we can draw those lines basically on our uv graph. So u is equal to 0, easy, or that should be v is equal to 0 on the bottom. U is equal to 0 right there, and then u is equal to v, just like that. Of course, we don't have a region, so we messed up somewhere. Let's see where we messed up. Anybody catch me? Anybody? Oh, this should be y is equal to x squared plus 1. There we go. So y is equal to x squared plus 1, so there should be a 1 on this side, and then we've got a u is equal to 1. Boom. So then this shouldn't be u is equal to 0, this should be u is equal to 1. And then we've got our graph, u is equal to v. All right, cool. So now we've got a region. And now all we have to do, step 3, is put everything together, and then we can solve the problem. So let's put everything together. We have a triple integral. We have our function, which we already solved, is 6v over 1 plus u cubed. And then we can go dv du. Something I've noticed with all these problems, because I think I've done 4 or 5 of these, 6 of these today to get this session prepped. I've always seen it dv du, and I guess I never noticed it when I took the class. But every example problem I've seen stays in the order dv du, which maybe you start with dv du every time and then go the other way if you need to. So we got dv du, and it's only double integral. So let's look at the u bounds. The u bound, we go from, let's hear it. Yep, I just heard you say it, 0 to 1. Okay, and the v bound, we're going from 0 to, yep, v, great job. All right, cool. So we just set up an integral. Now we can solve it if we want to. We could not. You'll get natural log of 2. We're already halfway through the session, so we'll keep moving if we can. But yeah, cool. It just requires a little bit of u substitution halfway through, nothing crazy. All right, cool. Let's move on. So now I've got another one. I'm going to let you guys go for this one. I'll give you a good 5, 6, maybe 7 minutes. See how well you guys can do on this. Make sure you do dv du when you get to the integral, because that is what all the rest of these sessions will be. So yeah. All right, go ahead and find your favorite Spotify playlist, get it playing. I'll set a timer for 5 minutes, and I'll see how long that feels. And we'll come back then. Good luck. All right, that's about 5 minutes. So let's see how we're all doing. Jacobian, pretty quick, pretty simple. You get oh, I won't do it in black. Let's do different color. You probably have something that looks like 2x minus 2x, 1 and 1. And if you don't have it in that order, that's okay, because we'll see what you get here. Is equal to 2x minus negative 2x, which is equal to 4x. Cool. So that means du dv is equal to 4x dx dy, or dy dx. What order do they have it in? Dy dx. Let's do that. 4x dy dx. All right, cool. So that's your Jacobian. So that's nice because I see an 8x here, which means that 8x will go away when we go to du dv. So let's just convert this function into u. So we'll have 8x times e to the power of, okay, so this right there, that's equal to u squared, right? And then if we see the next one, minus 4 times u. Oh, my pen freaked out. Okay. And because this 4x is right there, when we convert this to du dv, because remember right now this is still dy dx, then that 4x will divide out that 8x and we'll get 2e to the u squared minus 4u. Cool. So we've got our inside function, du dv, or dv du. Usually it's in dv du. Okay, so now we have an inside function. Next up, we have to write the bounds. So let's write the bounds if we haven't already. I just rewrote the integral bounds down here so we could zoom in and actually play with it. Oh, there it is. Okay. So we have 1 is less than or equal to x, which is less than or equal to 2. Maybe I'll do it in a different color. Let's do it in green. 1 is less than or equal to x, which is equal to 2. Okay, cool. So we'll have 1, 2. We'll do it on double bound. So 1 and 2 to 2. So that's our x region. Okay, and our y region, we have y is greater than or equal to y squared. So y squared is going to be a graph, or y is greater than x squared. My goodness, it's been a long day. So we have a parabola, right? And a parabola, and it crosses at 1, and it crosses at 2 at 4. So it would be 2, 3, 4. So it would look like this. So that's our y is equal to x squared graph. And then we have our y is less than or equal to 8 minus x squared, and we'll do that in like blue. So y is equal to 8 minus x squared, so it's a parabola that crosses at 8, and that'll just be like somewhere up here. And it comes down and it crosses at, of course, 4 at 2, right? So this is like 4. This is 2 comma 4. So it's a parabola coming down and crosses right there. And we've got a nice bound on the left. So it's not pretty, but you can see our region is right here. In between, x is equal to 1, y is equal to 8 minus x squared, and x squared is equal to y. Okay, so we have a region, and now we need to turn it into u and v. So the easiest way to do it, just kidding. The easiest way to do it is we write out our basically our bounds on our line here. So we'll write out x is equal to 1. Our other bound is y is equal to x squared. And our last bound is y is equal to 8 minus x squared. Okay, just a refresher, so we have it down here. Let's write our u and our v. Our u is equal to y plus x squared. And our v is equal to y minus y squared. Oh, sorry. Y minus x squared, yes. Okay, perfect. All right, so now we just have to do our substitutions. Okay, so let's start with our x is equal to 1, maybe. So let's see how we did this. We start with x is equal to 1. tricky. These always evade me. So let's think about it. Now let's not start with that one. Let's start with y is equal to 8 minus x squared. I think that one's going to be the easiest because we have a v is equal to y minus x squared there. So we can manipulate this guy into being 8 is equal to y minus x squared, and then so that means we get v is equal to 8. Yes. Oh, sorry, that's u. The minus is no. Yep, no, it's v. Okay. So v is equal to 8. I don't know why I have u is equal to 8 written on my page. Oh, because this should be a plus when we move it over. So there's a plus. Man, I can't do any math today. So we'll move that x squared over to the other side. To do that, we have to add it. So we'll get 8 is equal to y plus x squared, and y plus x squared is equal to u. So then we get 8 is equal to u. Okay, so that's one bound. We're 1/3 of the way there. Okay, y is equal to x squared. I would say we just move the x squared to the other side, so we'll get 0 is equal to y minus x squared. So that means we get, remember that y minus x squared is equal to v. So then we get v is equal to 0. Okay, that was pretty easy. Okay, the last one, x is equal to 1. These are always kind of the trickiest ones. This took me a minute to get myself. So let's look at it. So if x is equal to 1, we'll have u is equal to y plus 1, v is equal to y minus 1, right? Because I'm just plugging x is equal to 1 into our u and our v. So I plug those in, and now we have a common term, y, in both of those equations. So let's solve for y. We'll get y is equal to, so it would be u minus 1. Then we'll solve for y on the other one. Y is equal to v plus 1. And then we'll set both of these guys equal to each other. We'll get u minus 1 is equal to v plus 1. And then now we have an equation in terms of u and v. And we just solve that for something that we can graph. So we'll get v is equal to u minus 2, or u is equal to v plus 2. Okay. So remember, that looks like a classic triangle, like we've been seeing everywhere else. So let's see if we can graph that. So we have u is equal to 8. That's just a line. 1, 2, 3, 4, 5, 6, 7, 8 right there. There's a line, u is equal to 8. Not a very straight line. Now let's draw our v is equal to 0. That one's really easy. I like that one. It's in red. Okay, and now we need our line. V is equal to u minus 2. So imagine y is equal to x minus 2, and we're just graphing that. So we'll have x-intercept of 2, and then we'll be increasing at a slope of 1, and we'll cross that blue line at, looking at it, be 6, I think. So it'd be 1, 2, 3, 4, 5, 6. And we'll cross at 2, 1, 2. So now we just have a straight line, just like that. V is equal to u minus 2. And boom, we have a region. Sweet. Now we just combine everything. I don't think I have a... Nope, okay, cool. So I'll just combine everything myself. I don't have a part 3 written down. Combine everything, so we have our inside function, which we solve for, is in the light blue up there, right there. So we have 2e to the u squared minus 4u dv du. So I don't know why I keep writing 3 integrals, but I do. It should only be 2 integrals. So our du on the outside, we're going from 0 to 8. On the inside, we've got v. So we're going from, remember, if we're doing that, it's like a vertical slice. So we're going from 0, v is equal to 0, to v is equal to u minus 2. Sweet. And now, of course, we can solve that integral, but we're already at 41 minutes, so we'll just keep moving. Oh, sorry, Nathan, I just saw your message. Yes. All right, cool. Perfect. So that'll be your answer. If you want to solve it, you can solve it. And if you solve it, you'll get e to the 32nd minus e to the negative 4th. It's kind of a fun problem, but it's not too bad. All right, cool. Let's look at the next one. Rewipe, do not evaluate the following integral. Ooh, this one's kind of fun. By using the change of variables right there. So you can obviously see the function is going to change pretty quickly. I didn't give you guys the steps. So remember that Jacobian, and then function, and then boundaries. Let's do the Jacobian together, and then we'll move on. So the Jacobian, we have j is equal to, we can say it's like ux, uv, vx, vy. This should be a y, not even this. Okay. Cool. And if we solve that, we'll do ux is equal to 0, uy is equal to 1, vx is equal to 1, and vy is equal to -1 plus 2y. Take the determinant of that, we'll get the absolute value of 0 times -1 plus 2y minus 1, which is equal to -1, the absolute value, which is equal to +1. Perfect. So that means that du dv is still equal to dx dy. So we don't have to do any conversions, which is really nice. And now let's do our function. So I'll let you guys do this. Part B, function. And then part C, bounds. I'll let you guys go for about 4 minutes, and then we'll come back together right before the session ends, and I'll give you guys the answer. All right, good luck. All right, sweet. Let's look at this together before we run out of time here. So if you did your function, you would turn your function, it would basically turn into 1 over 1 plus v squared. Hopefully you got that just from the v function. Slides perfectly into the denominator there. All right, so that's our bound, or our function. Let's look at the bounds really fast. We've got, let's see. So we're going from 0 to 1 in the y. 0 to 1. And then we've got a line which is y, or x, is equal to y minus y squared. And that's basically a parabola on its side. It crosses through 1 and 0, just like that. So that's x is equal to y minus y squared. And then we have x is equal to y. That's a really easy line. So x is equal to y, just goes just like that. Okay. And then remember that our line was y is equal to 1, which looks just like that. So our region is right there. All right, cool. So now we have to write our bounds in terms of u and v. So doing that, let's start with x is equal to y. That'll basically say that u is equal to y. And remember that v is equal to x minus y plus y squared. But a little tricky here. Because we said x is equal to y, that means these guys cancel each other out. So we'll get v is equal to y squared. So now we have v is equal to y squared, u is equal to y. So we can say that by substitution then, v is equal to u squared. Really nuanced, really tricky. It's the hardest part of these problems is getting these u and v's right. Our next one is x is equal to y minus y squared. So we can look at basically our u and v equations. I see the v one is pretty enticing for that y minus y squared if we bring those to the other side. So we could say that x minus y plus y squared is equal to 0. And that looks exactly like the equation for v, which is perfect. V is equal to 0. Okay. And now we need one more. X is equal to, y is equal to 1, excuse me. So y is equal to 1. That's really easy. We left the easiest one for last because u is equal to y, which is equal to 1, so u is equal to 1. So we could draw that bound region really fast. So u is equal to 1, which is right here. This is u and this is v. And then we've got v is equal to u squared, which is just a parabola that crosses at 1. And then we've got that right there. So there's our region. Oh, sorry, other way around. Okay, and now we have a triple integral. We just write the bounds really fast. Our function is 1 over 1 plus v squared. And dv du, because that's probably the easiest. I wrote triple integrals again. What the heck is wrong with me? So we've got du, it goes from 0 to 1. And then we've got v, which goes from 0 to u squared. Okay, a little fast at the end there, I'm sorry, but I hit it right at 6 p.m. at the dot. So yeah,